Hello, good evening. Good evening, people who are from India and from others. Can you hear me, guys? Let's do a quick round of sound check. Can you hear me? Okay, right. Okay, you can see my screen as well, right? Yeah. So before we begin, can you guys if you haven't done it, please download the mnistrain.csv file from this link. The link is already available in the um, um, so the link is already available in the chat window. Okay, right. And please ensure that your practice lab environment is up and running. Okay. Awesome. So we will not start with this, but however, let's do one thing. Let's start our session. We had a very interesting session yesterday where we went through, quite a bit of things. And let me shift to the slides, and we will actually take it. Let's start with what we did yesterday, right? I think that is so. So what was the key takeaways that we did yesterday? Let's just do a short round of refresher course on us, saying that what did we do? We went through a description of what is intelligence, how do we model intelligence, what is artificial intelligence, where does machine learning fits into all these things, and what is deep learning and its goodness that we are going to get out of it, right? We've sort of tried to define our these terms, artificial intelligence and deep learning, in a more structured manner so that we can tackle and try to dig deeper into these constructs, right? We've also gone through a historical timeline of artificial intelligence, and we found out that this is not a new area of research or implementation, right? We have seen that even before a proper computer was even developed, human beings were trying to model intelligence, right? This is probably one of the oldest fields, and that sort of makes us humble and grounded, that we are actually trying to learn something which is being which is at its hem for a long time, and there's a lot of constructs that is there, right? We have seen a lot of successes. Okay, we now understand that deep learning, machine learning plus its new avatar of deep learning, right, is all around us, isn't it? And we see that its implementation across major products that we use on a daily basis at a scale that is almost unprecedented, right? And we see that it is really adding lots of values to our um, uh, this. So there's a question that, can you do in Anaconda notebook? No, you should not. There is you can do it on your own, but right now in the class, what we will do is like there's a Jupyter Lab environment where Simplilearn provides everything. You don't have to install everything. It's a full-fledged cloud-hosted Jupyter environment. So someone is saying that they can't hear sound. Can you guys confirm that you can actually hear the sound? Just one more time, guys. Yes, you can. I think Sapna, can you please check your your speaker system? Maybe there's a problem with your speaker. Yeah. Awesome. Thanks, guys. So what will yeah. So what the reason why we will not use uh, Anaconda is that it's tuned to your local environment. We want to ensure that all of us probably work on the same common environment. Similarly with Google Colab as well. Okay. So what this environment of Simplilearn, the practice labs, gives you is it's actually a Jupyter Notebook environment similar to Google Colab. So in Google Colab, Google manages it. In this case, Simplilearn manages it, and it ensures that all the right libraries, all the right things are already there. And if there is any confusion, there's a problem, Simplilearn support, IT team can actually help us by looking at their logs. Okay, so that's the reason, and it's also just and helps us to be on the same ground. All of us will be on the same ground. That's all it is. Otherwise, it's a Jupyter notebook environment. Both Anaconda and Google Colab is a Jupyter notebook environment, right? It's the same thing in this case itself. We will use it so that we are all on the same page, right? So that's a practice level. I think I showed you yesterday. Okay. And so what did we do otherwise on yesterday? We went through this idea and went through this a specific use case. One of the many use cases that we've deep dived is self-learning cars. And the reason we sort of we deep dived was that the fact that since modeling intelligence, while we are driving towards modeling intelligence from basically human intelligence, vision is one of the very important task one has to model, right? And the use case of self-driving cars or cars which drive on their own is a very complicated vision problem. It's not only vision problem; it's actually beyond vision problem. And we have seen that people who actually attempt to solve self-driving cars, they not only just create a solution for that specific problem, they create something fundamental. They create end up creating something which is fundamental, can be applied in many other areas, right? So that is one of the reasons why self-learning cars, the use case of self-learning cars is so important and so hot, because it's a complex problem. It's an AI complete problem, right? We have not spoke about the other important aspect of human intelligence, which is language. We have touched upon it. We will not spend a lot of time on this course, but please realize the fact that language is one key cornerstone of our intelligence. We are intelligent because of the significant portion of language, and that's also a very important area of all these algorithms, right? We've also looked at a typical life cycle of a deep learning project. We've realized that problems has to be solved, whether you use machine learning, statistical measures, or traditional machine learning, or deep learning. There has to be a way to do it, right? And that way doesn't change too much, though there are some optimized way of handling deep learning projects, and we've looked at some of the in a very initial framework around it, right? We've each other asked a lot of questions, and we've tried to understand that. Let me actually quickly share that we try to understand that traditional machine learning has a capacity. So do we need TensorFlow today? We will need TensorFlow at the end. We will just introduce it. We will not need TensorFlow today. Okay. However, yeah, so what we will do today is that we will try to unravel what is a neural network looks like, and I'll come to that. Okay, what's our course objective? So this is what we did yesterday. Let's go to the fact that what did we do? What did we do? This is done. So let me just go to the. Let me share the other presentation. Okay. Just 1 second, guys. Okay. So this is what it is. Okay. So I'm sharing it again. I'm sharing my screen again. Okay. So what we will do is now we will actually go through, today's agenda is very clear, right? Today we will actually deep dive into the construct called as artificial neural network, right? What are we going to do? We will focus on what are the building blocks of making this kind of things called as artificial neural network, right? And we will do it in such a way so that we can understand each of them in its foundation level, without any frameworks, without anything. If anyone asks us to build a normal neural network using just pandas and NumPy or normal functions, can we do it, right? That's one thing. That also one way to actually learn something, right? To break it down to a bare minimum or bare minimum, yeah, essentially a bare minimum component. That's what we will do, and we will introduce ourselves a little bit to the framework that we are going to do, which is TensorFlow at the end. But what we will do fundamentally is that how does all the different elements of a neural network looks like. And if you have already done machine learning, you will realize that all the core components that we did, that we were very familiar with machine learning, that will continue to remain same, barring there are some updation, okay, barring the core learning algorithm, the way it changes and the way it creates the learning function. Yesterday we spoke about parametric functions and parametric learning algorithms and non-parametric learning algorithms, if you guys have remembered, right? Do you guys remember what is it? Can anyone tell what was parametric functions or non-parametric functions in the world of machine learning in this context? Right. So if you take, no, that's not coefficient. If you take a linear regression, right, and you say that, okay, I'm going to solve a problem of machine learning using linear regression, right? Which by definition, which means that you already know the equation or the formula via which you're going to you're going to make your decision boundary, right? At its core level, every machine learning algorithm in the world will try to make a decision boundary, isn't it? It's going to cut the data, categorize the data in some form. And that form and that formula is given by the equation of line or a hyperplane, or a plane or a hyperplane. Essentially, it's a generalized form of line, right? If you have many features. So you already know the equation via which you're going to slice and dice the data in such a way that they are separable, isn't it? So that's linear regression. Similarly, logistic regression is the same thing, right? You already know the equation via which you're going to cut the data, or basically you're going to create your decision boundary. That's again the hyperplane equation, right? Go to SVD, go to naive Bayes. You already know the equation, right? In case of decision tree, remember, there is no such equation via which you're going to cut it. At every node, it's going to decide something, and it's going to construct a tree, right? Essentially a decision tree, right? So there is no fixed equation. So that's another class of algorithm where you do not know what is the equation that you're going to take, what is the formula, what is the functions, what is the shape of the function that you will use, right? So those are called as non-parametric equations, right? Non-parametric functions. And in this case, you will see that neural networks are non-parametric functions. There is no fixed shape from the very beginning. As and when we go through the learning process, the functions get complicated, and they start to build on their own, right? So, and that's what we will do. And while we do that, we will see that what are the core tenets, what are the core components of building a neural network, and that is something that we will start to see. Okay. We will also do, that's all of the exploration of neural networks, and we will do it in the way that we will do it till the time we actually understand it very well. Because like anything, if you have done machine learning, you realize, right, how many lines of code do you need to write a machine learning code? Someone answered it yesterday, right? Do you remember? Like, you have to do a model.fit, model.predict, basically 3 lines, right? Or most of the things is handled by whom? sklearn, if you are using sklearn, is handling inside it, right? But so if you're going to start by using the library on its own, you will not be able to learn a lot of things which is obfuscated or which is abstracted by the library or the framework that you're going to use, right? So it's better to actually understand them and then make use of the framework, so that if there is a problem which comes, you should be able to debug it, right? You should be in a position to debug them and get your desired output. Hence, to understand anything, we need to go to its root level, and then from there we should start using tools which helps us to gain something, right? We'll also go through this idea of back propagation, but I don't know whether we will be able to finish all of them together today itself. But if we don't finish, it's okay. This is a 4 hour class, and our class is for 3 hours, so it's okay if we, it's okay if it spills over to tomorrow. We are not in a hurry. Our objective today is to understand very well what are we going to do. Okay, the tenets of building a neural network, right? We will also look at and discuss basically regularization parameters, and how do you regularize neural network, and as you know, and we will discuss why do we need a regularization in even machine learning, any of the machine learning, why do we even need machine learning, regularization, and we will discuss all those things, right? Any questions on what do we want to learn today and basically part of tomorrow? Is there any question that are we clear that what we are going to do? Awesome, great. Okay, all clear? Okay, so before we start this class, I want to touch base on something that we did yesterday. Okay, and let me actually share yesterday's. So let me actually go back to our discussion that we were having yesterday, right? Remember? So till now everything was fine. We have this awesome machine learning algorithms, right? Linear regression, logistic regression, naive Bayes algorithm, KNN classifier, right? Decision trees, XGBoost, yeah, and there's a bunch of things, right? We ended up with SVM, and there are various types of SVM. There are SVC, SVM, but fundamentally it's all support vector machine, right? And we've realized that definitely people have realized that that's not enough, right? So let's try to go back to that point on time when people realize that it's not enough, and let's try to understand why people were thinking that it is not enough, and what is this, why are we trying to always look for this best learning algorithm. If you take any machine learning, right, take any machine learning pipeline, what are the three most important algorithms that we need? Can anyone tell? We would need to have a learning algorithm, right? Right? What is your learning algorithms? Like whatever we name, right? Can be supervised, unsupervised, right? We also need to have something to do with a loss function, right? Loss function is also an algorithm, isn't it? Cross entropy, binary cross entropy, and so on and so forth. These are nothing but an algorithm to compute loss, isn't it? So you need a loss function, some sort of loss algorithm, right? Loss compute algorithm, right? Given the fact that we still want to, we are still in the land of supervised learning, right? In unsupervised learning, loss is a little bit different, right? We don't know how to compute loss. And this is also given the fact that, we are assuming that if to learn, we always have to have loss. I don't know whether, I think there are ways. We have seen one of the other algorithms, right? Remember reinforcement learning, and there is loss, but there is also something from a feedback from an environment, right? It's a different kind of learning, right? It's actually a little bit better than supervised learning. And then someone was also talking about semi-supervised learning, right? So in any typical machine learning problem, you will see that we have the core learning algorithm. These are nothing but, what are those? This is my linear regression, right? LR, my logistic regression, right? LR, which is LRC, right? Let's just see. And then we have our SVM and blah, 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 right? This is my core learning algorithms. My loss compute algorithms. Do we know? Can you name one or two loss compute algorithms? Anyone is fine. Anyone? MSE, but good, very good. What else? This is actually, means square error, right? For regression, right? R2, very good. What is that we have for, classification? MAE, very good. What do we have for classification? All are regressions, good. RMSE, very good. So what do we have for classification? Binary cross entropy, very good, right? And we also have a, categorical cross entropy, right? And we might have other things also. So these are all loss compute algorithms, right? But this is not enough. We saw that, okay, this is good, but we don't want this loss to be computed at an infinite time. We want to learn faster, right? So we generally also would need optimization algorithm. What do they do? Their objective is to ensure that you compute the loss faster than you should be, right? Because you cannot take endless time, right? It's not possible. So what are the typical optimization problem that you have? What are the optimization, do you know? But before, okay, and so basically, let me just do loss compute, and then um, so optimization Adam is fine, but Adam is what? OLS is what? OLS is a loss function. OLS is an algorithm, right? Or for loss, right? Isn't it? Right. So optimization is what? Optimization is GD, gradient descent, right? And or for that matter, any flavor of gradient descent in SGD, stochastic gradient descent is a flavor of SGD. Adam is a tweak of core gradient descent to ensure that you merge faster, right? But fundamentally, it's gradient descent, right? LibSVM is not, right? Right. LibSVM is not. What is LibSVM? LibSVM is something else, right? But essentially optimization is gradient descent. Now, someone said that regularization. Where does regularization fits in? And we will talk about this, okay? I will say that regularization fits in somewhere over here, okay? And this is a little bit important. We will say that evaluation. Under evaluation, not exactly evaluation, eval if overfit, right? If overfit, right? Is regularization, isn't it? What is the objective of regularization, if you remember, right? So we have to have regularization algorithm, right? This is good. So we need to have regularization. How not to become overfit. Our interest is that we should never become overfit. And if you actually see the generalized formula of loss function, the final loss function is actually the actual any of this loss plus a regularization function, right? So essentially it penalizes the loss. If you are too much if you are learning extremely well the training data, what will happen? Even if your loss is low, it will penalize and make your loss high, right? It will say that you have not learned, you have learned too well. This road that you are trying to learn on this road, you have learned every pothole, but that is not the objective, right? So regularization is basically to focus on whether you are generalizing well or not, evaluation. So this is good one. So we have various many regularization algorithms, L1, L2, L1, L2, right? And there are some specific things only for neural network, which we will see, right? But L1, L2 is very common, right? We will see that we have ridge and lasso, both are L1, L2, right? So in case of linear, and in optimization is the gradient descent algorithm. Code is this. However, there are optimize as in like there are some variations of gradient descent because to handle the quantum of data that you can actually do, and of course there's a certain amount of complexity. That's about it, right? I mean, if you actually see that there are other aspects of it, but to at its core, and you can say that before learning algorithms, what happens? Even before learning algorithms, something else happens, right? We speak about data, right? We speak about feature engineering algorithms, right? Your feature has to be good, right? You have to be your all features. So there are some algorithms that you can use, normalization techniques. These are all techniques like normalization or projecting feature at a higher dimension, right? Polynomial feature, okay? So and so forth, right? I'm just saying normalization, scaling, and all those blah blah blah, right? So these are the basic stuff, right? So now this was all fine, and then we see that okay, there was at some point people were saying that this is not good, this is not sufficient. So what happened? Let's look at this quick example, right? Suppose we have this x and y, and we have discussed it yesterday, right? Suppose we have this x and y, and x is 0.5, 0.3, 1, 1.2, and similar the corresponding y is 0, 0, 1, 1. If you plot your x and y, and you will see that clusters of x's are separately, they are separable against y, right? You can actually put a best line. There's no problem in this. Your linear regression or any kind of linear model would work Absolutely fine. There's no problem, isn't it? However, suppose you have a data set like this. It's very simple, right? I have a, you can imagine this data set. X in this case is features and Y is my target, right? Y is my level, right? So, and my objective is that given a new X, what will be my Y? Any objective of any machine learning functions, what is that do that they do? They try to draw a decision boundary and try to find the relationship between X and Y in this case, right? So as you can see, right, if you actually plot the x's against the y's, the data points you have 0, 0 here, 0, 0 here, and 1, 1 here, which means this data is clearly not linear. No way it's not. It's linear. You cannot use a normal linear function to get away with it. We need some complex function, isn't it? Some sort of function which will actually looks like something like this, right? May something looks something like this. So what we did, we then actually what you will do, you will run this particular x and y via some sort of feature engineering and create a higher order feature in a higher dimension, and then you will try to do linear regression. SVM exactly does that, right? It will create some non-linear features, isn't it? Remember what SVM does? It will project this x and y at a very high dimension using a nonlinear functions called as there are multiple nonlinear functions, either is polynomial or something else called as RBF, which is radial basis function, and then it will do linear regression, right, or some sort of linear modeling, right? But the point is that we would need something complex. It's a line is not sufficient. And let's now look at this data. How can you even draw a line? How can you make it separable? More complex function, no linearity whatsoever. And now we have moved from a line to some other type of function which has a shape of a curve. Now the question here is that if you start from if you are thinking from a parametric standpoint that yeah, I have to draw a line always, then that means you have already lost the plot for this data set, isn't it? Because you know for sure that whatever you do, it is very difficult to draw a line and get clear separation in this particular data set, isn't it? So you need to do something, and that was the nemesis. On top of that, we know that typically data has outliers, data has other sort of distribution problem, which linear models are very, very prone to, and we should not be, we will not be able to handle it. You can go around it, but it is not possible. Plus, then if the data goes really, really large, right, and it's difficult to find a way to handle it, right? So now if this is my problem, and then that is where people started. So this was my basis of problem, and at some point till some point SVM was good. People used image classification even on SVM, okay, using language also. If you see the earlier spam not spam kind of a use case used to use naive Bayes actually, okay. This is a long time back, okay. They used to use naive Bayes and it worked at that time. It's fine, data was small, okay, but now language is everywhere, right? It's really, really large. Not only English, right? You have millions of different languages with own construct, and you need one generic model which would do this. So complications have increased, and this idea that linearity is not good, and you cannot have functions which ultimately does linearity will be a problem. And then the idea that human beings doing this feature engineering and generating features for machines is also not a great way to handle such large data sets. And that is where people have started thinking, okay, how does human beings do it? And how does human beings do it? Human beings have this kind of, structural things in their brain which are called as biological neurons. And if you actually look at a biological neuron, right, there are 3 or 4 things that we have to be aware about, right? There is this core cell. So this is the part which is the heart and soul of any a neuron, right? This is where it stores its energy. It's called cell nucleus, right? This is the cell itself, and it has some dendrites. Dendrites essentially are extension to nerve cells which receive impulses, which means they are a way to take input. Okay. Um, and then, so input signal is always generally comes from left. It's easier for us to actually demonstrate like this, but then generally there's one side the input is coming, dendrites accept that input. This is actually a physical biological neuron. This is exactly what it looks like. And because of that problem that we've seen, right? So researchers were really exhausted. And how many new models that we have to do, and at its core, still we are dabbling with linearity and various other problem statements, right? So, like, why don't we actually look at what our human brains do, since we are trying to even anyway model human intelligence, and that is where they came out, right? And they spoke with a lot of neurosurgeons or neuro professors, researchers, and they found out that the architecture of each of the neurons looks like this. We have input, which are dendrites, are processed via cell, and then there are axons, which are nerve fibers, right? And they transmit the outputs essentially, and axon terminals basically give the output. So it looks like, right? It looks like that, you know, it looks like that this somehow works. Like there is information which is coming in, right? And then something is happening in this cell. Whatever is happening, we are not yet there, but something is happening in this cell, and then it goes to various other different outputs, right? Now, now this was something that people try to model it, and in 1943, this paper from Vannon McCulloch and Walter Pitts, this is the paper on perceptron, okay, was published, where they said that we can actually have an artificial neuron which resembles something like this. We have a lot of inputs, in the way that these dendrites are, and then there is this circular thing, something happens there. Sorry, um, one second. So something happens here, right? And then we have an output, and we will define what happens in this circle. Okay, don't worry about it, but we will define what will happen in this circle. But for now, we can actually have an artificial neural network in this model, right? Um, Fair enough. So what then can we actually say artificial neural definition in? It is at initially it was definitely analogous to biological neuron when people started with this, where each neuron takes some inputs. Okay, let's go back to the image again. So each neuron will take some inputs, right? It will add some sort of weighted sum or weights, some sort of weights. Okay, each of this line means something, and each of this line can have weights, and there can be n number of inputs to it, right? Basically, it can be connected with n number of other sort of neurons, right? And then some sort of aggregation process will happen, right? So once you get so many inputs, something happens, and there is only one output which comes out, right? This output is very clear, right? There's a lot of inputs comes in, something happens, there is a one output that comes, and then output is distributed to, different types of connections, right? So that is exactly what an artificial neuron looks like at its very core. Um, just to sum it up one more time, an artificial neuron is analogous to biological neuron. At its start, I don't think nowadays it's in it at a neuron level, maybe yes, but overall neural networks have sort of deviated from whatever we have in our brain, I guess. But where each neuron takes inputs, adds weights, sums them up, and passes this through a transfer function called as a nonlinear output. This is interesting, and we will come back to this. Looks like that whatever is happening inside this cell or inside this neuron, this artificial neuron, there is some sort of summation happening, and then there is some sort of non-linearity that is happening, right? So that is exactly what happens. Now let's try to equate our biological neurons and artificial neural side by side to find out some sort of analogy, right? The cell nucleus is nothing but each node. Dendrites are my inputs. My synapses are nothing but my weights or interconnection. Weights are nothing but what can I learn, right? And my axons are my output, right? And we will actually go deep inside this, into each of the neurons. But overall, at some point this is what each of my neurons generally looks like, right? So this is where we actually introduce what a neural network is. Essentially, a neural network is nothing but a connection of many such neurons placed in a manner where they can take many sort of inputs and give an output to it, right? If you actually, let me just go back to this particular structure of a neuron, right, and explain to you in detail, right? Maybe this might help, right? There's a lot of you can see my screen, right, guys? You can see my screen, I hopefully. So if you see this circle, right, there is a lot of this lot of xi's which come. These are nothing but inputs, right? And they have, each of them, these connections have weights, right? And what happens is that each neuron, one single neuron, first there's some sort of aggregation operation, because since I'm getting a lot of inputs, I need to aggregate them via some formula, and we'll come back to that. And after that, I have to pass it via a non-linear function, right? A non-linear function, and this is what a construct of each of the neuron looks like, right? Do you have any questions on this? Any questions, guys? Awesome. Okay. What is weight? Great question. We'll come back to that. Weights are nothing but, okay. What is a weight? Weights are nothing but, okay. If you are aware of linear regression, what is the formula of linear regression? Oh, sorry. What is the formula of a line? Let's go to what is the formula of a line. If you are trying to model y equals to, can anyone tell what is the formula of line? Y equals to mx plus c. Perfect. So what does it mean? What does it mean? It means that the relationship between y and x is defined by this equation. It means that the relationship between y and x, so if I know x, and then I can easily know y if I know m and c. In this case, one thing is clear: c is a constant, right? M is also, c is a constant, right? It is also termed as bias. M is what? C is also a different name, right? Of course, y is dependent on x via this formula, right? This is the formula of a line, right? So M is nothing but a slope of, right? It's a slope, right? Slope means what? What do you mean by slope? If you are in a coordinate geometry, and then slope is something that at what point that it's cutting the y, right? Not dy dx, not yet. It's, yeah, of course it's a gradient, but here what I'm trying to ask is what does this aim indicate? Okay, what does this aim indicate? What does this aim indicate? Aim essentially is a coefficient. Aim is that some sort of, so if I actually have a question like this, y equals to 5x. Now I know that any value of x will be multiplied by 5 to get, any value of x will be multiplied by 5 to get my value of y, right? It's okay. I mean, if just get the intuition, Preeti, it's fine. You don't have to learn the math, but if you get the intuition, right? If you just get the intuition right, I think it is fine. What I'm trying to say here is that this relationship between y and x is defined like this. A generic formula of this is that y equals to mx. M can be of any value, right? And essentially, what I'm trying to say here is that if you actually generalize this, which means that plus 0, right? That's what it means. And so we can say that some sort of weighted multiplication of x with a constant number is the value of y, right? So m can be said as slope, or it can also be generically said that it's a weight for that particular x. You have to put a weight on x to get a value of y. That's all it is, right? It's just not on its own. X is not on its own. So when you also say something like this, suppose you say that y equals to x, so that basically means y equals to, what does it mean? Y equals to 1 dot x, right? That's what it says. And the weight factor is nothing but 1 here. Think like that, okay? and weights are always associated with my features, right? And this quantity is nothing but, this quantity is called as my bias, which means biases are not associated with my features. For now, just understand this. M represent the weight. Yes, exactly. Yeah, M represent the weight. So weights are always associated with my features, right? That's remember, right? And you can also name it as slope, C is intercept. Again, when you talk about slope and intercept, that means you are already gone to the line equation, right? So I'm just trying to make you aware that if you think from a parametric point of view, you already are in line, then slope and intercept makes perfect sense. In the non-parametric world where there is nothing called as line, you don't know even the function. So everything is generally called as weights and biases because there is no line, right? I mean, like you are not drawing a line. You're going to draw something which you don't know. The equation will be derived as the machine is trying to find the feature, isn't it? So there is no preformed line formula to start with. But weights are something that you always apply on features, right, to get some value. So in this case, it's x, and this is what a machine learns, and we will see that what is a learning, what does a machine learn at the end. These numbers, this m and x, weights and biases, is what machines learn. When someone says that, we saw that one of the slides yesterday, one model was training at 300 billion, 600, 300 million parameters, right? So those parameters mean that there are 300 million weights and biases, literary numbers in the model, which can define the function. Can you now comprehend that idea that we have 300 million coefficients? Right, exactly. So that's what it means, right? When you say that there are 300 million parameters, these M and C's are what the machine finds out. That's what it means, and that's why it is such a complicated piece, and we will come back to that. It's definitely, oh my God, but what I'm trying to say is that you can understand that. That's just nothing but a bunch of numbers, right? It's like 300 million numbers in some order, and they form a large equation, a large function which the machine found out, right? I hope I'm able to make it very clear. Good. So now what happens is that let's look at one algorithm which was actually the implementation of this algorithm was like in 1943's paper of Pitts and McCulloch, right? We will see that there was one specific algorithm called as perceptron, which was developed, I think, about 10 years after that. If you actually go to the Wikipedia page, the machine was 1957. Yeah, right. Thanks for that. And the machine was a huge machine, and it was a image classification machine. They wanted to build a hardware around it, but the way they did it is this, right? This was the first instance of a neural net kind of a thing, with one layer, and we'll talk about what are layers. So what they did is that, so they have these features x1, x2, x3, x4, and these are nothing but image pixels, and they will have lots of weights. We'll talk about what is one. Okay, this is the weight 0 is always the bias. Okay, we'll come back to that. We'll come back to the input function and activation functions shortly. Okay, we will look at each of them in its own merit and try to understand them very, very well before we do our thing. Okay, so now what happens is that, so for this, first is the inputs. In each of the inputs are assigned some sort of weights, like x1, x2, x3, x4 are nothing but features, and the W0 is nothing but the bias or the C term, if you have to relate with y equals to mx plus c equation, the C term, right? And W1, W3, W4, whatever it is, are all related to x. So it's going to be the M term, right? And then something happens. This net input equation is nothing but a summation operation. Okay. What happens is that we will sum something. Okay. You will add. Essentially, what perceptron did is that they will simply add all of them, right? They will do a dot product of each of them and simply add. Nothing but this is a summation operation, right? Right. Okay. What happened? Okay. And then the output of this. Reason for summation, my objective of my each per neuron was that what I'm trying to do. I'm trying to model this neuron, right? I have lots of inputs, and I have to output one one value, one output, right? So what am I trying to do? I'm trying to model this particular neuron in the spirit for in its own way of biological neuron. So what I'm trying to do, what is perceptron trying to do was, it was it was taking all these features, all of them are getting multiplied, there was summation operation happening. Okay, and I will explain this, don't worry, we will actually look at the code. W0 is the bias, yes, that's correct. So we will do a summation operation and then we will do an activation operation. Activation is a non-linear operation. Remember, we said that we have defined the neuron like this exactly. What did we define the neuron? Each neuron will sum them up. Each neuron takes inputs, adds weights to them separately, sums them up. Literally, it's just addition, nothing else. Plain and simple addition. It's like plus operation, okay? That's it. For every weight multiplied by that particular input, and then pass this final summation value through a transfer function. This transfer function is nothing but a non-linear function, okay? A non-linear function like this, which gives my output. So this was perceptron, and if you actually go down, you will see that this is what used to happen, right? X1, X2, X3, these are my features, right? Everything is numeric, yes, all are numeric. Everything is number. Computer doesn't understand anything about number, hence a machine learning model, any machine learning for that matter, doesn't understand anything about numbers, right? So what used to happen is that the perceptron main processing unit, there used to be one neuron. So one neuron looks like this. Do the summation. So x into W1 plus x2 into W2 plus x3 into W3, whatever the value you have, you also have that bias, right? And then pass it via function called as activation function or transform or transfer function and get the output. We will look into all those things, right, in detail. So this was perceptron on its own. And while the weights determine the slope of the equation, right, this is what we are talking about. While the weights, they do determine the slope of the equation, right, some sort of slope, the bias shifts the output from the left to right. This we will actually take a call, and yeah, so this is correct. So basically x1 plus x2, w2 plus x2 plus w2 plus dot xn dot wn plus the bias term. There is a bias term as well. That is my summation operation. If you have to look at what is the final summation operation, let's just go here. And so this is my summation operation. So the first part of aggregation is sum of dot product of all of x dot w, right? Sum of dot product of x dot w, right? Plus a bias operation, right? So this is at its core the very fundamental. And then this function is some sort of non-linear function, and we will look at it. There is a very finite set of non-linear function. We will look at it. You already know one such function. Can you guys tell me which machine learning model uses a non-linear function at its last layer? It's a very popular model, by the way. Sigmoid operation. That's correct. Sigmoid. Logistic regression uses sigmoid. Sigma function or sigmoid, right? Sigmoid is a very popular loss activation function or non-linear function, and believe it or not, it's been used here also. Nowadays we don't use it for whatever reason. There are reasons, but you should know that sigmoid is a non-linear function, right? What do you remember? What we used to do in sigmoid? We used to draw it used to project against 0 and 1, right? It creates an S curve, right? Let's look at some of the activation functions, or these are also called as transfer functions, right? Remember that these are also called as transfer functions, right? The other name of activation functions is transfer function. But however, once you actually start building out things, you will see that they are mostly called as activation functions. So this is a step function. There are already three functions that have been shown: step function and sign function, right? Either it is 0 or it is 1, right? That's all it is. A step and sign are very naive function. People do. Sorry. Keep on moving my mouse. I'm extremely sorry about that. Step and sign are like this, and sigmoid is something that we can use it. Can we use neural networks for regression problem too? Absolutely. It's a all-purpose generic algorithm. Absolutely, right? So there is no so anything which we can do classification we can use regression for, right? At its own, at the end we can All we have to do is just, rather than computing the probability, compute the real value. Don't compute the probability, right? That's what it is, right? So these are some of the activation functions. We will go through other new age activation functions. Step and sign are definitely no more used. Sigmoid is definitely used in places, but there are other better activation functions which helps with non-linearity aspect of it, right? Okay. What's the time now? Okay, we are coming towards. Shall we just quickly do a perceptron use case? Yeah. So let's do one thing. Let's do that, right? And you will see. Let me actually go to. So I've just gone to. You can see my screen, right? I just gone to sklearn. People who are familiar with sklearn, you will see that there's a perceptron implementation already there. Okay, why it is there? People don't use it, but it's a good implementation for something which was so ancient, right? However, from a perceptron point of view, remember that it had only one layer, right? Let's do one thing, guys. Let's open our practice labs quickly, and for the first, let's open our practice labs quickly, and let's open the assisted1.ipynb file. Okay. I'm going to give you a couple of minutes. I have opened it. I hope you can see my screen. Let me actually refresh it once so that my notebook is almost 50 minutes. I think it goes for inactivity. Let me just reload it once. Please go to your LMS and open practice labs, right? And I hope you have actually downloaded the MNIST dataset. What we will do is, like, using that CSV file, we will actually build a perceptron model using the sklearn implementation of it, right? This is the sklearn implementation of it, right? Just to give you a feel about it. And this will also allow me to understand how many of you are ready with practice lab and so on and so forth, right? Just give me a shout out once you guys are done so that I can start. I've got one yep. I need some more yeps. What is the link to download the datasets? Can someone please paste the dataset link? Thank you, Nisha. Yeah. So I'm going to give 30 more seconds and then we will start. Okay. It will be good if you can actually code with me, and it's a very simple piece of code. Okay. You can see that it's done, right? That's it. But we will try to just make our hands dirty and code ourselves. I would highly encourage you to code whatever you see it's okay. And I strongly believe that if you have to make your hands dirty and code and make errors, because that's the only way for you to learn. Remember, without a loss function, it's very difficult to train ourselves, right? So you need to have a loss function, and you need to create an environment where you actually make loss. So this is the environment where you will make loss and you will produce errors. Okay. Sorry, what? So am my screen not visible? Okay. Is it too small? Too small. Are you sure that you are full screen? I hope you are not. Is it too small? Okay. I think it's probably can you actually increase your size? Then it will be better, I guess. But if it's too small, please let me know. Large file size. Yeah, it's about 105 MB. So you can simply download it, right? It's just a file. You can download it and say yes. Yeah, exactly. I'm just upload it here. Okay, I think let's do this. Okay. So what we are doing is that we will try to build perceptron model on a data set called as MNIST. Do we know what is MNIST? Can anyone tell what is MNIST? It's a revolutionary data set, right? What is MNIST? We should know what is MNIST. Shall we look at what is MNIST? Yeah, okay, good, no worries. So what is MNIST? MNIST is a, no, it's just not any other image data set. It's actually a handwritten image data set. And this was created by these three guys. One of the guys whose name is Yann LeCun. Yann LeCun is chief AI of Meta right now, okay? He's one of the legendary guys in deep learning, machine learning, okay? And you guys, we all should follow this person. He is in LinkedIn, okay? And you can follow, and he keeps on. He does a lot of work on. So basically, you can see, right? He's a legendary guy. So MNIST essentially is a digit of handwritten database, right? It is it looks something like this. I don't know whether you can see it or not. I will show it to you. Don't worry. So basically, it looks something like this. Okay. So it looks like yeah. So this is how it is, right? It is. This is each of the data looks like. Okay. There are 60,000. There are 60,000. I will send all the links. You can also do Google for MNIST. Okay. Just MNIST Yann LeCun, done. The first link that you will get is Yann LeCun. This is a this is a very old data set, and you can get it, and though it's very small and toy data set, but for us to understand, this is perfect. Okay. This is assisted one. That is correct. It's a good question. It is assisted one. Yes. Assisted one. Yeah, we are in assisted one. I will not do assisted two. I will actually show you something else, which I will actually take you through this particular thing for instead of assisted two. This I think is much better. Okay. So what is MNIST? MNIST looks like this. Okay. Handwritten data set. Our objective is to identify them, right? So this is what it looks like. Okay, you can look up the literature of MNIST, and you can see that Yann LeCun in 1998 has used linear classifier, pairwise classifier, KNN. Okay, and let me just drop a note. Okay, so this is an SVM, and this is his idea of how he did it. Right, 1998, two-layer neural network, 300 units mean square error. Right, now you will know that two-layer network is, what is a two-layer network? Is it a shallow network or a deep network? Can anyone tell? It's sort of, nowadays it's definitely a shallow network, right? But think about this, 1998, 2000, Mr. Hinton was also contributed to this, right? So I think, and then it went on till 2012. People have used all those things. So just have a look at it. Just type MNIST. The first hit you will get is Yann LeCun's page. It's worth going through it. Great. Let's just go through that. So this is the data set. We are clear on the data set now. Okay. All I'm doing is bunch of imports. What I'm doing, I'm just importing NumPy, Panda, Matplotlib. Okay. Do I need Matplotlib? I don't need Matplotlib here in the assisted one at least. Where do you get assisted one? You will get assisted one in your self-learning under, if you actually go to your live classes. So this is the thing that I told yesterday, right? When you go to self-learning under your lesson 3, right? Under your lesson 3, right? And you can get this thing. This is assisted one, 3.4. You can download the code here, right? Linear classification perceptron. Okay? Yeah. And similarly, you can also download 3.7, 3.8. Unassisted is something that you can do. And this is how it will be. Okay? This is how it will be for all of them. In fact, if you see, your practice project is also here. It comes with its own data set as well, right? This is also MNIST, but this, you should actually use this. I think it's the same data set, right? Okay. What is the objective of this assisted one? Objective of assisted one is to check how the implementation of a perceptron neural network, was on this particular data set, and get ourselves acclimatized that we can do the coding in this. Okay. So let's start, guys. Okay. So I've just executed the first piece of code. I'm just doing bunch of imports. You can do import NumPy, import Panda, import Matplotlib, and you can do import sklearn, sorry, linear model from sklearn, and so on and so forth. What is 3.7? This is Python version, is it? It's fine if you have. What is 3.7? Are you talking about Python version? If it's Python version, it is fine. Right. So can you actually raise a support request as a part of this thing itself? I think on the course, not at the if you actually go to self-learning. Okay, let's talk about this. In the self-learnings, go to section 2, go to lesson 3. It's lesson 3, and then you should have lesson 3.4 and 5 and 6, right? That's what it is. So if you are not seeing other sections, please raise a support request. Okay. Let's continue, guys. So I'm just loaded the data. This is my data set, right? How does the data set looks like? This is nothing but a bunch of numbers. If you actually go to MNIST, right? MNIST has it's 28 by 28 pixel array image, fairly small image considering nowadays, right? It's 28 pixel by 28 pixel, which is 784 pixels, right? And if you actually see this, so this is actually all of the thing. If you actually load the whole of data, so this is my head looks like. So where first column is nothing but my so this is this column is I'm seeing head as a value. Head is not a column in this case. This is actually what it has done. Panda is that it has considered this also as a column name. This is not true. Okay. In this case, the first column is nothing but my class. It indicates that what is my digit, and rest of them are a collection of 784 pixels all stacked together. Okay. Let us have clarity on what is happening here. Okay. How did this happen? So how did this happen is this. Okay. You have an image. I'm just going to quickly show. Sorry. You have an image, right? You have this image. How do you represent this image? This image is actually divided into so many places, right? So many things. All right. And this is true for your any kind of device, even if your television or any display for that matter works like this. Each of these things are the lowest possible unit of a graphical display, and they can be attributed by they are nothing but pixels, right? There are electrodes and other things which actually draw the pixels, right? So an image can be represented like this. If an image can be represented like rows and columns, and each of these values can be between 0 to 255, and we will actually discuss what is the value of 0 and what is the value of 255. If it's a black and white image, this will be one dimension only, like just a one row, some bunch of rows and bunch of columns. However, if it is a color image, what's going to happen is that we will have something like this. So you understand what I'm doing here? So we will have, sorry, let's just do it like this. It's better that way. So we will have 3 channels. Okay, this is for blue, this is for green, this is for the other channel, RGB, red, blue, green. Okay, that's how image is represented. But removing the complexity, we don't have that complexity. It's a grayscale image. We call it as a grayscale image. MNIST is a grayscale image, black and white image. It is represented by rows and columns. In this case, there are 28 of this, 28 of the rows and 28 of the columns. So in a sense that how many such, the whole image, one image can be represented as like from 0 to 28 into 28, which is 784 values. So essentially what's going to happen is that you can have a big array of total 784 values representing one image. Am I making myself clear? So this whole thing is nothing but, am I making myself clear? This is a very important thing. This will give you a sense of how you transform something like an image or anything into number. There are various different techniques. This is one of the techniques, right? You need to transform. Remember one thing, any machine learning model in the world cannot work unless it is number. How 784? How 784? Can anyone tell how 784? That's correct, right? So let's go here one more time. So this is essentially, let's make it small. This is essentially 28 rows into 28 columns, right? If I actually move this into a one array, right? One continuous array. So it will become an array of, total array of size, one array of size 784, right? Is this clear? Now is this clear? If I actually move all of them into one array. So essentially in other way, if I actually paint like this, right? Why 28 only? That's a good question. Okay. We can ask Mr. Jan LeCun, but however, in this case, this data set, the images are 28 by 28 pixel. Okay. Why? I think there is a reason why they, they wanted to representation. They don't want it to work with a large image. Okay. This is also, you can imagine, right? This is 1998. And it's pretty old data set, right? So this particular data set has 28 by 28 pixel, just to work on it, right? But however, that might not be true. But this is you can imagine how small this image is, and this itself is such a big number, right? Now, total number of features have suddenly exploded, right? You can imagine how complex then our images right now is, because we have 2000 by 2000, right? Each of those images will be like millions of features, right? So this is how an image is represented. And we can actually put an image. So what's done is that all those pixel values are most of them are 0. Some will be 1. Some will be little bit. Some will be somewhat closer to 255, because 255 is white, 0 is black, right? Like that, right? So essentially, if you see this 5, most of them is black, right? And let's see one with the big one. See, this is one specific image for 7. All the things are most of the pixels are black. So most of them will be 0. Some part will be really white. Some will be little bit of white. They will be some values between 0 and 255, and some really which are bright, they will be 255. That's all it is. Okay. This is an important understanding for us to know how we transform an image into numbers, and that's how we do it. Okay. That's how it also gives you an appreciation of the fact that with a simple image like this, we are talking about 784 features, right? That's pretty large, right? All the things that you have done with real life features, they did not have so many features by himself, right? So this is a high dimensional data on its own, right? Great. So we have loaded the data and we have looked at the data. We have understood the data, that we have understood the importance of this particular data set, and that it has 784 features and one target. The target is the first one. 9 is represented by this, 1 is represented like this, and so on and so forth, right? Okay, fair enough. Let us create a data frame of x and y. What is my x? Everything which is target. What is my y? Only the target, right? We have segregate, right? This is still a supervised learning problem, right? Someone has painstakingly done this. So I do my df and xy. I have already imported train test split. Do we know what is train test split? Anyone wants to answer that? You can take as much as time, okay? We are not in a rush. I just wanted to ensure you all understand this. Do we know what is train test split? Train test split essentially allows you to create training and testing samples based on your test size, okay? Whatever you want, and it is considered to be representational of the actual data set. Remember that, okay? So if you do this, splitting data is hard, right? It is not easy to split data. You can say that, okay, I will only take top 10, so maybe top 700, and then rest I will take as test. But it is possible that you might not be sampling them properly. Train test split allows you to do that, right? Fair enough. Cool. So I've got my X train, X test, Y train, Y test. Now what I'll do is like I will simply install Perceptron. What is Perceptron? Do we remember what was Perceptron? Let's look at Perceptron. This is Perceptron, isn't it? Perceptron had so many inputs. So how many inputs there will be now? How many X's? 784. Perfect. And there will be, sorry, I don't know. So and there will be one. So each of them will have 784. One, yeah, there is only one hidden layer in Perceptron. There is only one layer. Perceptron has only one layer. That's it. Okay. The implementation of Perceptron. So another of the input will be the bias term. Okay. So inside Perceptron there will be two parts to it. There will be an aggregation operation which will multiply each of these weights with the features, and then we'll say, by the way, what will be the weights? We will actually see. Do you see the weights? We don't know the weights, right? Have you given the weights here anywhere? You just divided to X train, X test, Y train, Y test. You haven't done anything else, right? Then what you do is like do Perceptron, then you do fit. In the fit, what you have to do? You give your X train and basically you give your features and the corresponding labels, right? You did that, you have, and it's training, right? So now it's actually fitting the data, right? Let it go, and then we will see. I don't know how long will it take. Okay, so it's done, right? So it has given me an object, right? It has fit the whole data, 60,000 of it, right? And the model is ready essentially. This is the model which is actually ready. Per is the model which is basically ready, right? To predict now, right? So what just happened with one line? I was able to train. What happened internally? This is exactly what has happened. It has multiplied each of the 784 features with some weights, and by the way, we have not passed the weights. It has computed the weights, right? Then it has done this operation of addition or aggregation. Then it has passed this output via an activation and gave an output. That's all it gave, right? And if I quickly see the test set, let's just let's take oh yeah, so or let's take what is X test 0, right? So there's no point in saying this, right? This is X and small x test. So X test is of Panda data frame, right? Okay. Right. So let's take, so these are all my values of 0. Let's take dot ilog, suppose 100 is not there. Yeah, it's there. 34,006. The class. So let's now look at Y test. Ilog 100 is nothing but 0. Okay, so 0 is this is the image of 0. Now if I actually pass the whole of X underscore test, I've got a prediction of all of them. I will see that the real predicted value. This is nothing but a. By the way, what is this type of classification? What is the problem statement that we are doing? Can anyone tell me? This is classification or regression? It's a multi-class classification. Perfect. Trying to find out, and classes are, how many classes we have? We have 10 classes, right? 0 to 10, and that's what we did, right? And you can see that we will do a little bit of evaluation. Let's find out how many predictions were correct or wrong. We found out that 10,464, and let's try to find out the prediction. So our model accuracy is around 0 to 9 is nothing but 10, right? Our model accuracy is around 88%, which is, now given the fact that this is fairly simple, not that bad, not that great, no comments whatsoever. Question is that were you able to run this in your Jupyter Notebook lab, in your practice labs? That is more important question. Yes. Okay, I've got 1 yes. Can I see some more yes, guys? Thank you. Some more yes, yeah. Because this will tell me, right, that you are there, and when we actually go to higher order things, we should not be worried about Jupyter lab and so on and so forth. We should focus on the frameworks and all. So are we clear what we just did? We have just trained a model called as perceptron. It's a linear model. It looks and behaves a little bit like neural networks, but is nowhere near neural networks. It's very early model, one of the 1957, it's an implementation of 1957. And let's look at its API documentation of sklearn, right? I always actually go to as to how to let me do that. Okay, let me do that in a minute. Okay, I think this is important. If people are there others who are facing the same problem of how to go with lab part, because this is extremely important, folks. Okay, this is extremely important. In fact, I would strongly suggest, can you go to your course introduction, go to lesson 1. Okay, you can see my screen, right? Go to course introduction. This definitely you have, and there is a video that you can look at it, accessing practice lab. This you must be doing it before coming to tomorrow's session. Okay, this is a task on you. Okay, Shobha, please do that. Okay, and then if you still have a problem, we can look at it. So what we did, we just trained a linear classifier using perceptron, which looks and behaves like something like this, and it's more or less giving some output, right? Fair enough. Let's now look into what is this feed-forward networks. Okay, we are now going slowly deep into the domain of neural networks, and we are trying to. So, what is this question? Can you paste the link of scikit-learn link? So, scikit-learn link. So, sklearn. Just go to sklearn. That tab should always be open. By the way, guys, huh? You should always ensure that tab of sklearn is always open. Okay, I will drop it. This is the perceptron link. Okay, I will also drop the other link on MNIST. Okay, this is the MNIST link from Jan LeCun. Okay, you should look at the literature and read it. These are the good things. And sklearn, you can go and look at, just do a search here and you should be able to look at it. Okay, so let's move on. Let's move ahead and try to understand this term called as feed-forward networks. Now that we have understood what is perceptron and we have just executed one of our things, some students don't have assisted one, assisted file. Can you please raise this with the LMS team? You should have. You must have. Okay. The assisted one, assisted file, this thing. So essentially, this is here, guys. Okay. If you actually go to 3.1, it's 3.4 and 3.7 and 3.8, right? That's what it is, right? That is what we have, right? Is it possible to display what? Regarding the weights of perceptron, is it possible to display? Yeah, I think it's possible to display. So let's look at that. Perceptron, so attributes, classes, let's say coefficients, right? So we'll go here. It's a good call. Okay, so we can do per dot coef, I think, right? Coef underscore, right? So this is my coefficients, right? So this is all my coefficients, right? And how many coefficients are we talking about here? Let's do a learn. Okay, we have 10. Yeah, so it's basically a linear model, right? So ND array sets, if it's n classes, weight are assigned per features, correct? And then, so Nisha, please raise a support request. Okay, please raise a support request. Yeah, thank you. Right, and let's look at intercept. So we have got coefficient, and why are we talking about coefficients and intercepts? Because this is a linear model. Remember that. So this is my intercepts, right? How many intercepts? Okay, how many intercepts, guys? One intercept. How many dimensions are we talking about? So number of weights is no number. 784 is what? 784 is number of features. Remember that, right? Right. 784 is number of features. Your per coefficient is 10, and your intercepts are 10 as well, right? That's a good call out, okay? Whoever called out, thank you very much. And you know what? It is perfectly okay if you don't remember that per.coef underscore. Nobody can actually remember that. So what you should do? You should always have your API documentation of that particular neural network open. And this is something that you have to continuously do. TensorFlow, when we go to high order TensorFlow, do not try to memorize these things. You need to open API documentation, go through it, and and apply it. It's okay. You have to understand what's the crux of it. Okay. Perfect. I think. What are the other questions that we have before we call out for a break? And post break, what we will do is that let's realize what post break what we'll do. We'll go through feed forward networks. Actually, let's finish this. Okay. Let's finish perceptron. There's some more perceptron that is left, and let's look at the problem of XOR problem, right? That we are getting, right? How intercept is 10? Okay. How is intercept 10? Can anyone tell how is intercept 10? Constant in decision function. ND array intercept will be as many as number of classes, right? How many dimensions you have? How many dimensions do you have? As many as that many dimensions, right? That is what you have. That is what perceptron does. So essentially, though it's an output of 1, right? Ultimately, it's still a multi-class classification, right? At the end, it will do a probability of any one of that, right? So the way it does it is that you will have so many number of coefficients, as many number of class, and for every such class, if it is that many number of intercept, right? What is also important to understand is that since we are talking perceptron, let's talk about what is the loss function that it uses. You can see that concrete, at least this implementation of perceptron, right? Nobody uses perceptron. You don't have to use perceptron in your production, okay? This is just to understand that something that is so revolutionary has happened long time back. It is just for you to get acquainted with, right? So this is a concrete loss function that determines the loss or the difference between the output. This is a simple difference between output and input. Okay. Fair enough. Great. So let's close perceptron. So let's come back to slides and let's finish couple of slides left for perceptron, and then we'll go to a very important topic, which is post this thing, and then we'll also look at neural network. How do we build a neural network, right? So what is feed forward network? Essentially, for a network, perceptron is actually a feed forward network, right? Which is where is a very big difference between the current neural network. Information can only go forward, okay? It is distributed, though it is parallel, but it is unidirectional from left to right. In current neural network, what happens is that not only you have information which goes from left to right, which means that if you actually see this image, right? If you actually see this image, let me show you this image, right? So information is going from here, input layer, to some hidden layer, to output layer. It also comes back, and there's a reason why it comes back, which we will discuss. But in case of perceptron, that is not something that happens, right? So it's only a feed-forward network. That's called as feed-forward network. A perceptron can learn anything which is separable in the hyperplane. Of course, it is it is a linear classifier, right? It's actually a linear problem. However, it cannot represent an XOR problem. Can you guys tell me why it cannot represent XOR problem? How the number of neurons present in the hidden layer is decided? We go through a process called as hyperparameter tuning. Okay, there is no fixed set. It is up to you. Okay, you decide how much you want. There is no formula which will actually tell you. Generally, we actually go through a part called as hyperparameter tuning. Okay. However, there are established problems which has there are ways that we can do it, but there is no equation that will tell you. It's basically you have to trial and error. There is nothing else. Okay. However, let's come back to this. If you see the XOR problem, right, and this actually resonates with what we were seeing, right? If you have an X1 and X2, right, this is what sort of problem? Is this a linear problem or non-linear problem? Can you guys tell me? Is this a linear problem or a non-linear problem? Why? Why is it non-linear? Where is non-linearity coming into picture? Where is, in simple English, can anyone tell me? It's a, okay. Someone is saying linear problem, okay? Why it is linear problem? Why it is non-linear problem? Anyone? What is the linearity? What do you mean by linearity? Linearity means you have a trend, right? If I grow, you grow. If I don't grow, you don't grow, right? There is some sort of trend, right? Do you see there is any trend? Yeah, basically, yeah, you can actually draw. That's the reason, right? If you can put things on a line, but line is a very mathematical representation of it, right? The moment you bring line, hyperplane, it's easy to get confused. However, what I'm trying to say is that when you say that you and me are linear, means that whenever you go, I will also go, or whenever you go, I will never go, right? If there is never a case that sometime you will go, I will go, and some other time you will go, I will not go. No, right? So conditions don't change. Whatever you do, I will have some sort of static, static logic of doing things. It doesn't change. XOR is anti of linear, right? It is basically anti of linear. So basically, you can see that if you have minus 1, you have minus 1. If you have 1, 1, you have minus 1. It is almost impossible to solve a linear equation like this. If you have a relationship, if you have things like this, you cannot draw a line. Perceptron hence will fail miserably because it cannot handle non-linearity well, right? You can say, yeah, they are go parallelly as well. Yeah, they can go parallelly. In this case, it has been shown that they are going parallelly, right? In fact, if you actually give this data set, right, the data set that we were talking about, remember, where was we talking about, like this data set? Let's just, if we give perceptron this data set, right? Do you think it will work? It will not work, right? It's highly non-linear, right? It is just a made-up database, that data set that we did, right? It's highly non-linear, isn't it? Okay. So do we have multi-layer perceptrons? We can have multi-layer perceptron. We can actually add more than hidden layers, and we will look at it. What are these hidden layers? But however, the most common output function will always be sigmoid. What is sigmoid? We discussed about sigmoids, right? So we can have one input layer, and then we'll have multiple hidden layers, and each of those hidden layers can do the same operation, take some input, do this aggregation plus function operation, and then gives an output. The output will always be one layer, isn't it? So there's only one input output layer, and there are a bunch of hidden layers. Now, how do we build multi-layer perceptron? Let's come back to the API, right? And we see that it is possible to actually add multiple layers or not, right? So how will I add multiple layers? Is it possible to add multiple layer? Where am I seeing? So I'm seeing penalty, which probably refers to my regularization, and I don't see anything, right? So I probably, what I can do is, like, I can add multiple perceptron, right, after one after the other, but that is something that one can do. Okay. So this is what we just executed. Okay. This is nothing but the assisted one problem. So, and we've just closed perceptron. So perceptron essentially is a very naive representation of neural network, and we will see that it's a feed-forward only network. It has only one layer. One can actually build multi-layer perceptron, but not worth it right now. What we will do, so we will take a break now. We will take a break of 15 minutes. We still have 1 minute to go. When we come back, we will actually do back propagation. So we've discussed this problem, that feed forward network, right? The information goes from left to right. Your on your input to your hidden layers to your output. but we will see that what is this back propagation thing is all about and how does it helps neural networks, right? Maybe before that, what we can also do is like maybe we can actually look at the aspect of neural network itself little bit more, like what is this network, right? Like what is happening, what is input layer, what is hidden layer, what is output layer, what do we call this? Okay, that we can also look at it. Does that work, guys? And after this, what we'll do is like after we do backward propagation, we will look at a we will look at a notebook where we'll actually build neural network using simple NumPy and Panda and nothing else. Okay, so that we understand how one can build it. Yeah, absolutely. From tomorrow onwards, we will actually focus on TensorFlow, and Keras is now part of TensorFlow. Okay, we will on focus on TensorFlow itself. Okay, guys, shall we take a short break of 15 minutes? I'm gonna put the timer. Okay, thank you, guys. Thanks a lot. Let's come back in 15 minutes. Okay, I think it's time to get back. Shall we restart? Okay, guys. So let's start then, right? So um, shall I start? I think in the interest of everyone, let's start, right? So we discussed, what did we discuss? We discussed that we've got to an understanding that there is a neuron. Okay, we've not yet we still don't know what this neuron on its own does, but we will look at it. So sorry, we exactly know what the neuron on its own does, but in the grand scheme of things, what happens is something that we will see. But however, let's let's revisit what the neuron does. Neuron, this is like literally single neuron, takes a lot of inputs from the previous set of outputs, and it can be an input layer as well, or it can be something else also. Once, and each of those are nothing but features to it, right? These are xi to xj. Each of this, right? Each of this gets multiplied by a weight, right? Xi gets multiplied by its own weight, right? And so on and so forth. So each of these connections are being weighted, right? Essentially, in a way to say, and like when you say that, xi is of w1 weight and xj is of wj weight, it sort of represents is that if there are two different versions of, so two different numbers of wi and wj, it sort of represents how important xi is or xj is to this neuron, right? So suppose wi is -1 and wi is zero point 0.2, right, and wj is zero point 0.4. One thing is very clear, zero point 0.2 is less than 0.4. So you're trying to give more importance to xj in this case than xi, right? In a very localized form, right? In a very intuitive manner, you can understand something like this, right? Is that clear to you guys? Right? How important is each of the features across all the feature sets, right? And that is what a weight represents at a feature level. So what happens is that each of the neurons does two things. Um, First thing, it does an aggregation operation, and the aggregation operation generally looks like always this. It's basically a dot product of all the x's, which is the input, to its weights. And when we talk about machine learning, in this case, it's not basically all, it's basically a matrix multiplication operation. Okay, it's going to be a matrix multiplication operation, and we'll do a dot product of that, and we'll sum it up, right? And what we're going to do, we're going to add a bias term to it, right? So this is what the aggregation operation will do. The output of this aggregation will be going through a non-linear activity, okay? And this function, based on the quantum of functions or the function that you choose, right? So if you choose sigmoid will do what? Sigmoid, if you remember, linear regression sigmoid will actually create an S-curve, and it will reduce the value from between 0 and 1. Whatever the value of this aggregation is, it will reduce the value from between 0 and 1, right? If you remember, right? Similarly, there are many other activation functions, and they are also called as sometimes transfer functions. They decide as a whole whether the neuron is okay to fire or not, sort of, right? They will say that is it okay to fire or not, right? So that's what we do, right? So we do aggregation step or summation, right? And then the function part is also called as transfer or threshold. We saw on this, right? This is called the transfer functions or threshold functions, and they literally decide whether the neuron is fired or not. We will go through lots activation functions in a way, but there are, as you can see, there's quite a bit of activation functions, right? You know definitely sigmoid, identity, binary, and so on and so forth. These are very simple, and we know tan h, arctan, and so on and so forth, right? But the intuition behind is that why do you need a non-linearity? Because to represent non-linear relationship, to fetch out, to get what is the relationship between lots of x's and my output variable, I need some sort of non-linearity, right? I need to fit the curve, right? I need to somehow build my function in a way that it represents the data, not just always go with line. And as I do it, I'll understand more and more non-linearity, and that's how then ensure that I will not fall down into something which is very linear, right? This also gives me one other thing. Each of these nonlinear functions allows me to scale the output of a neuron. So this neuron's output, if I use a sigmoid operation, I will always know that it will be between 0 and 1. If I use a tanh activation function, I know that it will be between -1 and +1, because that's how the functions are, right? And if you see ReLU, right, it will be between, again, anything 0 and 1. And we will actually go through each of these things, right? So now, how does a typical neural network generally looks like? We will have something called as an input layer. Input layer looks like this, and we cannot consider these input layers as neurons. Okay, they are a special layer where you actually give the actual features, the features that you get it from the from your data set, right? And then at the end, and then in between, you can configure multiple hidden layers in this case, and each of these things will be connected like this. Okay, each of the features will be connected like this, right? And each of them might have your each of the connections, sorry, each of the connection that you have will have its own independent weight, right? And basically what they represents is that how important is x3, how important is x3 in terms of x2, right? So that's what it represents. So what are hidden layers? Hidden layers are the magic. It's the place where the magic happens for most of the neural network, isn't it? How to assign weights? Awesome question. How to assign weights? Right. So we will actually look at it. How do we assign weights, right? Initially, the weights are assigned dynamically. You don't assign weight, right? Did we assign any weights while when doing perceptron? We did not. We have no clue what is weights, right? How do we even assign weights? As someone who's building a learning logic, we should not assign weight. In fact, if you consider that weight is something that the model learns, then you cannot guide something. And you said that I want to learn driving, then you are asking the question that how do I learn driving? So the weights are never assigned, weights are derived by the model, right? That is the crux of it. You have asked a very fundamental question, but how do we assign weights? We don't assign the weights. Model derives the weights via this whole process of training, finding the loss function, finding how much is going to change, and going back again and update each of these things, right? But first understand that we have to start somewhere, right? We definitely have to start somewhere. So in the spirit of starting somewhere, the weights are at the very first epoch, at the very first time, they are assigned randomly. Okay, and then as your training cycle goes, the weights are adjusted, and you learn better and better. Your weights are updated, right? And the updation process is a two-step process. You go back. We will do that. We will actually look at what is back propagation, and back propagation is what Geoffrey Hinton, he did not invent it, but he has worked and made it sure, and there are other people also, including Jan LeCun, ensure that it is at a state where it is acceptable at a neural currently, right? So what happens is that we will look into that. So you take a pass, you have your first your weights are randomly assigned, right? These are a lot of weights. They're randomly assigned. You go till the end, you find out your loss function, you say that there is some loss that you have happened, right? Then you go back based on the loss function. What you do is like you change the weights based on something, and we will actually go through that. That process is called as back propagation, right? Back propagation has changed the world, okay? Because now you are able to assign weights or change weights at a epic scale, right? 300 million weights are changed, right? 500 trillion weights are changed. Think about it, right? It's a large network. You can change so many weights based on some loss function. That's tricky, right? And we will look into that. So bottom line is that we don't assign weights. Weights are bread and butter of the models. They derive. Our objective is to ensure that weights are somehow initialized randomly, and that also we don't do. The algorithms do. There are some algorithms which call as weight initialization algorithm, especially from Hamming-Hay, right? If I'm not wrong, Hay initialization, right, is a very popular. I think that's the de facto of TensorFlow. So there are algorithms which actually the way how do we initialize it. If you remember, if you have done k-means clustering, right? To start clustering, you need centroids, and there was a variation called as k-mean plus plus. The weights are assigned, that the centroids are assigned at the very far from each other, right? Something like that, right? Where you have to assign a weights in a manner it is inappropriate. How to find best activation function? We will know. See, the thing is that right now we will actually go through that right now. Maybe we can go through it tomorrow. But how do we find the best activation function? Right now, overall, ReLU is very famous. Everybody uses ReLU, okay, unless you have a very specific reason. And ReLU has other variations of ReLU, okay, to address certain problems, right? But most of the people use ReLU as well. And you can also build your own activation function, right? I have seen people who have built their own activation function. Okay? But ReLU is almost a de facto standard. Okay? It's not hit and trial. It's mostly, I think, sort of de facto. But coming back to the structure of a neural network, we have input layers. Each of these inputs are linked to my neurons. There are 3 layers here. This is actually a 3-layer. This is actually a 4-layer network. We will say it's not. So we don't consider input layer as layer because input is just input, right? And each of this will go through some sort of aggregation and some sort of activation function. Each activation function is per layer, right? Remember that you can define this activation function per layer. You cannot say that in this layer this neuron is one activation, this neuron is another activation, this neuron is another activation, right? Something like that. So that is at layer, and there is also a bias term. So then there is an output for this, and there is an output for this, there is an output for this, isn't it? So let's give a contrasting color. And then again this is an output for this, there is an output for this, there is an output for this, right? Similarly here as well, right? There's a lot of connections. These are nothing but dendrites, remember, right? Each of these have their own weights. So we have weights here, similarly we will have weights here, similarly we will have weights here, right? The idea is still same, right? How important is the output of this particular feature to this neuron? How important is the output of this particular neuron to this neuron, right? So that is what the weight signifies, right? And it's a collection of lots and lots of weights, right? And then at the end we add something called as an output layer, right? This output layer, if it's a classification kind of an example, so you will add a layer called as softmax. Remember, softmax is a very simple activation layer. It's a very simple activation layer. It basically says that max of what it does is that it will compute probability. It will give you a value of between 0 and 1 across all your classes, and that is what you need. For regression you don't have softmax. It's the actual value is what you need, right? How do you know what what each neuron represents? You don't, right? That's one of the reasons. At a scale, suppose of 300 million parameters, you can't, right? It is very difficult to know. So to represent that what each of the neurons represents, right? That is one of the reasons it is called as a black box model, isn't it? Where its interpretability is questioned. It works brilliantly, right? But at each neural level, think like this, right? maybe this neuron is, if you are showing him that image of 5, right? Let's go back to that 5 image, right? That's what we have seen. Suppose it's showing the one neuron, one layer might be looking at the edges, another layer may be looking at this arrow, that if it is trying to find there is a line or not. Okay, another layer might be looking at, is there any curve or not. Intuitively that is what it is. However, it's very difficult for us to actually comprehend what is this each neuron seeing, because they are just bunch of numbers as gets computed, right? That's why it's one of the reasons called as a black box model, right? Number of neurons is kind of hyperparameter, which is correct. Which we need to twin. Yeah, I think number of neurons, if you actually have larger number of neurons in your hidden network, hidden layers, it's good. This is also where I think one we should say that what is happening in this hidden layer. What is happening in this hidden layer is couple of things. Okay, remember, even in our practice labs, what did we do any feature engineering? And you will see that this is very common that in neural network we hardly do any feature engineering. Of course, if there are some features that you need to add, that's a different thing, because good features are always good features, there's value in it, but not much of feature engineering is done. So if you see, right, these hidden layers are in a way getting out the hidden feature representation, which is almost impossible for us to know. So these hidden layers are where the feature representations are refined and latent representations are extracted. Okay, that is what it is. Each layer would be of 700. No, not necessarily. Your input layer will be of 784, because that's what it is. You can actually have each layer of whatever, like 10, 20, 30, 700, 17,000, whatever. It can be 10 also, doesn't matter. So in this case, I have four neurons. I have 3 first hidden layer, right? So it's actually, I'm reducing it, right? So it's not necessarily that it has to be 784. 784 is my first input layer, which is my number of features. Remember that, right? In a layer, is it possible to assign different activation? For no, so that's what I said, it is not possible. In TensorFlow, so that is managed by TensorFlow. You have to specify, and you will see that when you code, right, you actually code per layer. You say that, okay, add this layer, and there are many types of layer. Add this layer, in this layer you have so many neurons, and this layer's activation function is this. Or you can say that add this layer with so many neurons, and this is the input. You don't even say the activation function, and then the next time you say that add a ReLU activation layer, something like that. Okay. So the reason that is happen is that from mathematical computational point of view, this operation of aggregation and function doesn't happen at a neuron level. It is if you realize what I'm trying to say, right? Do you think that this is computationally very effective if you actually do it at each neuron level? Because these are all numbers, right? You can actually represent them as a matrix, right? And you can do it at the whole layer level itself, right? You can do it full thing at the whole layer level itself, yeah, at an overall level itself. Hence, it makes sense to at a layer level, right? Because it's a large matrix multiplication. Essentially, this equation, sum of dot product of x is a matrix, right? What is my matrix size? X is, what is the size of my x in case of my MNIST? What was the size of matrix x? 784. Now, the question is that it's actually not x, it's the transpose of x. But what we did is that it's the x at the row level, right? What happens is that in matrix multiplication, if you remember, go back to your basics mathematics, if you do put it in the column way, right, it gets easier to multiply, right? So what happens is that you transpose it and put the rows into columns. So it's basically one column, 784, sorry, yeah, one column, 784 rows, right? And that's what happens. And all good questions. Number of hidden layers are defined by us? Yes. Number of hidden layers is not dependent on number of inputs at all. Number of hidden layers is dependent on you, that how long are you willing to invest to find out latent features, right? How long? And there are, nowadays the models goes with 1,000 layers, okay? It's very common nowadays. If you see the models which have 1,000 layers, and So largest model is what? GPT-3 Megatron, right? How big is the model? Sorry, GPT-3 parameters. So you can see 175 parameters, 96 attention layers, 3.5 million batch size. So this is a model which is such a big model, 2 years old by the way, 175 billion parameters, right? So you can think like that, right? So this is all large model. So it's not dependent on you. Sorry, it's entirely dependent on you. It's not dependent on the input itself, right? By default, it's 10. Who decides the default? Who will decide the default? There is nothing called as by default, right? TensorFlow can have a default. PyTorch can have its own default, right? So user, yeah. So by default, it's not 10. It's not necessarily. It doesn't have to be. But the idea here is that the more deep that you go, you will try to find layers and layers of hidden information, and those hidden information are nothing but features. And once you have those hidden information, which is virtually impossible for any human being to comprehend, you cannot build any feature engineering technique to actually get those features, right? And then if you give it to your learning algorithm, and that is what you actually do, your machine learning, your learning, right? You create a decision boundary on that, is then it becomes really good, right? So from an intuition point of view, remember that this summation operation and this sigma, sorry, the non-activation operation happens at a go. It's a matrix multiplication, all right? And basically matrix operation, right? And hence it has a layer level. So it's easier because you can have a array of features, which is one array of weights. You just have to multiply. That's it, nothing else, right? Okay. Shall we look at backward propagation is my question. I think we should look at backward propagation. We should actually not look at in a way that is, let me see how it is there. Let's just get the understanding of it, and then we'll actually go to the we'll see what is backward propagation and why it is important, and then we will actually go to the one use case, and that's where we can see the other things. Okay. So what's backprop? Okay, in short term, it is also called as backprop. So it's you say we saw that the feed forward networks from input to hidden layers to output, it is always going. But essentially, yeah, it's a feedback path, right? I know now. I know I came here, right? All of these are like what? This is my final layer. My final layer is generally a probability layer if it's classification, isn't it? Now, how did I know that this is exactly? So they give an output. What do they give? They give class 1 or class 2. That's it. Nothing else, right? So they basically give a probability of class 1 and probability of class 2. Whichever is the best one, you choose that one, isn't it? That's what you do. So this neuron will say that based on this way, the class 2 probability is 0.2. This neuron will say the class 1 probability is 0.8. Right, and the combined joint probability of all of these neurons output will be 1, right? That's what it is, right? How did it come to that? Because it at this moment, at this output layer, it has applied that your loss function, the cost function, the error function, whatever you say, right? That you had your Y train, your Y true, the gold values, the true values, and it did that computation, right? And typically you use either binary cross entropy or cos entropy. We can look at that. Maybe we can actually look at a loss function and the understanding of loss function itself sometime, because cross entropy is a very interesting algorithm on its own, and it's used so much everywhere. I think we should understand cross entropy from an algorithm standpoint. Okay, it's used heavily everywhere, including neural network, even if it's such a simple algorithm, right? So at this time, we have already computed the loss function, right? And you know that some way that what is your loss, right? Now the question that remains is that, okay, you know the loss, first, how do I create this feedback path, right? It's a very good word that you said, right? And improve on this thing, right? I know that I have made an error of 50%. But how do I now improve it in such a way that all these lines, these dendrites, or in other ways, these weights and these biases can be updated? And that logic and that algorithm is called as backward propagation in a neural network, right? What it does is that it initializes. So what does backward propagation does? It has multiple steps, right? At very beginning, it has initializes the state, right? Weights, right? You remember, right? When I started with it, right? When you started the first one, we have initialized the weights, right? Someone has to initialize the weight. So backprop initialize the weight and threshold, right? With some value. We don't know what value it is, right? Sorry. Then it provides the input and calculates the output, isn't it? X will be, so in this case it has, this is the output that is given here, and then it calculated the output, right? Essentially it has computed the loss, and when it computes the loss, right, so it knows now that suppose, this value is 50%, the loss is at 50. Now what it does is that it goes back against all of the weights and try to find out if I have to reduce my loss. Again, objective is to reduce my loss, how much each of these weights have to be changed. It tries to find that, find that equation, or find that idea that if I have to reduce my loss by some small amount, how much of my weights have to be changed? Which all weights, sorry, not which of, how all my weights will be changed in terms of value, right? And this is where we will use we will use a lot of calculus, because study of change in mathematics, study of change is nothing but calculus, isn't it? Like if you are if you want to change a little bit of y or little bit of y, what will be my value of x, right? That is what I'm trying to say. If I'm going to change a little bit of loss, what will be my value of weights? But at the end of it, everything in a neural network, for the matter anywhere, is dependent on these numbers, right? Your weights and biases. So you're at the end you have your weights and you have your loss output, as in like 50% loss, 30% loss, 20% loss, right? So that reduction is directly dependent on those W's, various W's that you choose, right? So the equation or the path which finds out how much I have to change my loss, such that, and what will be the value of, if I change my loss by a little bit, what will my value of weight should be, is called as, is basically uses form of derivation, divide s, but is part of backward propagation. And then once it does it, it literally updates the weights and then repeats the whole process of training. Now that it knows that, okay, if I change the weights in, like if I change these 100 weights like this, I will actually accomplish a loss reduction of suppose by 0.2 value or something like that, and it will do the whole thing again. So that is at its core the backward propagation is all about, right? So there's two very fundamental important things that we should know. We just knew that, we just now equipped ourselves with this understanding that there's something called as backward propagation, and it is very key. And we have also understood this term called as feed-forward network. Somewhere with feed-forward, and in other ways you can consider that this part or this operation, right? This operation is nothing but a forward pass. They are also called as forward pass. Okay, a forward pass is nothing but this operation: aggregation plus a sigmoid operator. Sorry, not a sigmoid, an activation function, right? While a backward pass, when I say a backward pass, which is nothing but a backprop, is the operation when that you have already computed the loss and you know that you have to reduce the loss, and then you have to find out how much weight should I be reducing to achieve a certain amount of loss, right? So these two are very, very fundamental. And if you see now, if you actually evaluate this with your classical machine learning, do you think this backward propagation Yeah, of course, right? Not only reduce, right? Why are you saying reduce? It can be increase also, right? You can say that X3 or this neuron was overly compensated, reduce this but increase this neuron, right? Yes, depends on loss and depends on the importance of each of the neurons lines, right? Each of the weights. Some neurons are important, some are not, and that will tell you. So for each of the loss, we compute that for each of the W's, and that's a heavy duty operation on its own. The way it's computed is via a logic. It's called something called as chain rule. Okay, and we will look into that at some point, but it is very important for you to understand that there's literally two things happening. So this also means one thing, that if you're going to define a layer, right, every time you actually create a neural network layer, you must actually give an implementation of forward pass and an implementation of backward pass, right? The backward pass, what it all it does, it computes gradients, right? What is gradient? Gradients is nothing but the change percentage, right? It does not apply the change. All it does, it computes that change. Okay, it will not apply it. Okay, so application is not his objective. Application will be done later, little bit later. So it will just simply compute and keep it ready, keep the gradients ready. And this is not a trivial process, and there's a lot of mathematics involved, especially calculus, to do it. It's intuitively fairly simple to understand, but we'll actually go into the details of it. I'm sure there are a lot of classes where we'll have to see the details, right? Okay. Let's do one thing. Let's just quickly go through this. Okay, so this I will not go through this. What I will do is, like, I will show you a example. All right. Let's go through some code and let's do this thing. Right. What we will do is, like, we somehow now know a tenets of neural network. Right. If I ask you to build a neural network, you know enough to actually build a neural network. We know for sure that any machine learning learning in the world would need at least few things. It needs a learning algorithm, it needs a loss, it needs a way to compute whether it is overfitting or not, right? And it needs a way to quickly go to the loss function by using something called as an optimization strategy, right? But for our point of view, what we'll do is, like, we'll focus on the learning algorithm, right? And given the fact that loss compute is anyway already available, right? And what is my learning algorithm? This is my learning algorithm that we said, that have the features ready, okay, make a list of all the features, pass it via so many number of neurons, okay. Each neuron represents two operations, an aggregation operation and an activation operation. You can choose n number of activation operations. We will look into that. Let's choose whatever the simple thing that we have. We know sigma, we'll use sigma, right? Or we will use whatever we can. And then that is what is forward pass. Go through multiple such layers, right? We have to ensure that whenever there is an implementation of a layer, we will have to implement forward pass, and then also we have to implement backward pass, because we need to ensure that our weights have to update it. And then at the end, we'll have a probability layer. Right? Keep on track on the loss is 0. Yeah, that's a good question. Our objective is never to, is your objective ever to make loss 0? When the loss is 0, what does that mean? When the loss is 0, what does it mean? If you have no loss, which means what? Perfect. Great answer. Which means you have learned the road so well, you have learned each and every pothole. Your 99% of cases, your model it's not a perfect model, it's an overfit model. It will probably fail in a sense of it has memorized rather than learned. So our objective is not to actually go to the lowest 0. Our objective is to reach to a state where it has some balance. It learns things, right? And if you actually add the regularization parameter, it will not make it 0. It will start penalizing it, right? I think we now know enough to build a neural network, and let's look at that. How do we do it? Okay, and we will only use. Let me just see whether it works now. Okay, fine. Then we will use what do we use? Let me just, someone was saying that this was very small. I think this is really poor. Is this better now? I think it is much better than the last one. Okay, so let's do one thing. Let us now continue to have that same MNIST, and let's build a neural network from the scratch with whatever we know. Okay, we might not know a lot of things, but we know enough, right? And let's try to put all our idea and see where we actually land and end up. Okay, this, don't worry about the, this is not there in your course, but what I'll share this code. That's really simple. I'll share it. Collapse. How do I collapse? Oh yeah, I can collapse. Yeah. So this is the best I can go. Is that okay? I think it should be fine, right? Okay. So now let's do one thing. Let's just import NumPy, right? And let's build a class called as linear. In this class, let's do one thing. Let's take a constructor, click on the folder icon. Okay. Cool. Thanks. Okay. Okay, does that work now? Is this better? Okay. Is this better? I can't see the. Sorry, if I do this, the problem is that. So if I do that, right, what's going to happen is that I will not be able to see the comments. So let me do one thing. Let me go through this, and then we'll come back and discuss, right? Okay. So what we'll do is, like, let's build a class, right? And this class will name it as linear, right? Okay. And this is going to be a linear layer, as simple linear layer. We have done one thing very clearly, right? To become a linear layer, or to become a neural network kind of a layer, I at least need few things. What do I need? I need to actually take some inputs. I need to produce some outputs, and whatever happens in between. My forward pass is nothing but what? What is my forward pass? My forward pass will be, if I actually go here, just let me remind ourselves. My forward pass is this, right? Aggregation plus function, right? So what I'm going to do here is now that this is a linear layer. I don't care about my non-linearity part of it. So for now, what I'll do, I will only add this, right? So I'm going to take input size and output size, right? I will just randomly, so this is my weight initialization. You can see that I have just randomly initialized weights. How many weights I need, I can easily find out, right? See, if I have four features, let's go here. I have 4 features, 3 new nodes. How many weights I need? I will share the code, don't worry. Let's focus on this. If I have 4 features and 3 neurons as my first layer, how many weights do I need? Can anyone tell? And how many? Let's look at 12 plus 1, perfect, right? With one bias. So here what we are doing is that, right? Here what we are doing is that we are actually adding the bias separately, essentially, and W is like this, right? So we have in and out size like this, and we have ensured that we don't fill them with zeros. We've ensured that we fill them with some small value, 0.001. If everything is 0, then anything multiplied by 0 is 0, right? So you don't learn anything. So start with some non-zero value so that you go somewhere, you reach somewhere, right? You can start biases from 0, that's not a problem, because it's an additive information. And here, this is what my weights and biases matrix. I can actually create an array, which is nothing but like this, right? I'll keep my gradients of W and gradients of bias. This will be computed. When this will be computed? When I will be doing my backward propagation. For every such layer, I need to actually maintain something like this, right? And I also have to ensure that my input has to go back. So what will be my forward pass if I don't do if this is a linear layer? Remember, I will only do that aggregation part. What is my aggregation? Multiply my X with my W, add the bias. That's the only thing that I'll do, right? And if I do a forward of this, so I will simply, whatever the output of this, I will simply forward this. So function, create a function, take my input, given my input, compute my weights with this, multiply the weights, do a dot product. So this is how you do it. You don't actually do a for loop of features to neurons. You simply do a matrix multiplication. You can use np dot, right? It's a dot product. And in this particular case, what will be my backward propagation, or a backward propagation looks like? What is backward propagation? Backward propagation is to basically try to find out if my loss is changed, what it will be. Now, don't worry about what is this right now. We will come back to this. Okay, there is a dedicated class on this. So as of now, just understand that backward, to compute the gradient of, or to compute the change of W's, all we have to do is we have to do dot product of the x, which is the feature that is there, and by the next gradient. Okay, so this is my backward progression. Don't worry about it too much right now. I'm just trying to show you what it is, and then we can come back to this later, right? So this is a linear layer. Let's look at an activation layer. How does your activation layer looks like? And in fact, if you see, this is ReLU, activation layer. This is true ReLU's implementation. ReLU is exactly this. ReLU says that if you are passing me a value, that value is maximum of 0 or 1, or that value. Okay. In fact, if you see the ReLU's, so ReLU looks like this, right? Rectified linear unit. So this is ReLU. So let me just check whether we have a ReLU picture somewhere here or not. I think it is there. I just wanted to show you once before we. So this is ReLU. So this is ReLU. ReLU looks like this. It's actually everything is 0 or anything else. Like if it is greater than 0, take that value, or 0. So it will truncate anything to 0 or that value, right? So that's what we do. So this is literally ReLU's forward pass, ReLU layers forward pass. On the backward pass, there is no backward propagation for, there is no gradient computation for non-linear operations, right? Why? We will talk about it. So what I'm trying to say is that you cannot compute a, you don't compute a, gradient operation for a non-linear layer, or in this case the activation layer, right? And we will come back to that in detail, right? So this is literally what ReLU's implementation is. Fairly simple, right? I mean, you can actually get it. You might ask the question that why this, and we will have an appropriate answer at some point in time. We have spoken about what is softmax function. Softmax function is exactly that last layer, where what we do is like, it's also an activation function. However, what it does is that it helps you to generate probability for all, right? That's what it does. So this is exactly the equation of softmax. Okay, it basically does an exponential of x minus the max of x, right? And then divided by the exponential x. So everything using NumPy and nothing else, right? So softmax is generally always used for the last layer, right? Now what we need is that we have two layers. We have a linear layer. We also have a non-linear layer, okay? And we also have a output layer which will give us some sort of probability, isn't it? Because you might have given a lot of numbers, but I need probability, isn't it? But what we need now is some sort of loss function, right? How do we know that the model is doing loss or not, right? So we need to define our loss functions, and fairly straightforward way to define loss function. How do you define loss function? We can actually add something like this. We can add we just going with the flow. You can add forward and backward function. Okay, there is nothing called as backward in this loss computation. You can simply use softmax for this. However, for forward, all I am doing here is that this is my cross entropy loss of mathematical formula. Why and all we can discuss later, but consider that this is the cross entropies. This is the cross entropies example. right? Literally, like this is like 5 lines of implementation. We can explain and we can unravel when we discuss cross entropy. But essentially, this is what it is. And it gives me a scalar value. Loss is always a scalar value, right? It gives you a scalar value, right? That, okay, your loss is now 0.2, 0.3, 0.4, and so on and so forth. Your objective is to go down, go reduce yourself, right? And our objective is to, given this loss value, how will I change my weights? And that will be defined by my backward functions on each of my layers. This layer of linear will tell me how to compute my weights for that particular layer. This function of this particular class will tell me how to compute my weights for that particular layer, right? And that's that. I mean, that essentially is a crux of neural network in a very simple manner. It's fairly simple, but it sort of hits the story home, saying that that's all you need to an understanding point of view. This code might not scale to millions of examples, but at least it gives you a very good idea of what is what and what is not, right? You can not use, in case of ReLU, okay, in this case we are using ReLU, right? If you actually go to Assistor 2, and I'll actually keep it for you, you can see that tan H is also a activation function, and it is as simple as this. This is a simple implementation. Tan H, if you see, it goes from -1 to +1. It looks exactly like sigmoid. However, sigmoid starts from 0 to 1, tan H is from -1 to +1. Fairly simple, right? It's like, fairly simple and fairly easy to comprehend. Nothing very complicated about it. Now, what we should do is, let's use this neural network, homegrown network, into test. We can load the MNIST data using like this. Okay, Keras dataset has MNIST on its own. Okay, or we can load our CSV file itself. Either way, we can build our test and train features. Okay, and finally we have our X-train and Y-train. That's what we want, right? You can visualize it. So this is one of some samples have been visualized. You can use Matplotlib, has a function called as IMShow. If you actually give it an array, it will try to show what the image is, and that is what it is. Clearly are handwritten images, and these are nothing but labels, right? So this is a 5. I need to actually say that it is 5, right? For us, it's very easy, but this is a supervised learning problem, so this is the class. So how do I define the neural network class itself? Now I have independent things. I need to now join stuff, right? Let's just define the neural network class, right? I need to be able to have many layers. I need to be able to actually have a loss function. My neural network should have some sort of gradients for computation, and it should have params. Params are nothing but my weights and biases. I must have a function called as add a layer. I should be able to add many layers, right? Multiple linear layers, every time a linear layer and an activation function. Linear layer and activation function. Overall, my neural network should have a forward layer. What will the forward function does? It will go through all the layers forward function. Fairly simple, right? This is what it will do. What will be my backward function of the neural network do? It will reverse. It will start from the back. The backward prop will always start from, where will it start from? It will start from the back and go like this, right? That is exactly what it does. Given my list of layers, reverse the list of layers and start calling the layers backward at a time. That's all it does, right? And start storing my new gradient and append them, store them somewhere to compute them. I can actually do train, I will do predict, and I will do score. And this is my whole of the network. My ability to create a network is achieved, sort of, right? I would also need some sort of ways to update my, I need an update function, right? Update function which will actually update my weights. You can actually define something like this. Don't worry about this right now. But this essentially, what it does essentially is that it updates the weights, okay? And that's about it. We can actually have some more custom function where we can train it, right? Train it, all it does is that if you pass it the list of epochs for every such layer, it will build that hold of neural network class, train for X train, Y train, and do it accordingly, right? It will do accuracy, mean accuracy, and so on and so forth, right? And if you actually, let's just see what it is. This is how it is done, right? This is your neural network class, which is defined here itself. You can add a layer, which is the linear layer. You say that my input dimension is whatever 784. I am given hidden nodes of, or how many hidden nodes I have? You started with the first node as 32 neurons. Then you added a new layer called as ReLU. So after this linear layer, which is my aggregation operation, all you did is an aggregation operation, right? In this one, you add the non-activation layer, right? So this is the activation layer, which is the non-linearity. After that, you put another linear layer, right? That could be your output layer, and you just give it to train. And if you train it, you will see that this is not a bad model itself. And and everything else remains same. You can create confusion metrics, you can create prediction scores, and so on and so forth. But you will see this. What I wanted to tell you is that we will come back to this code again and again and again and again. This code is extremely simple for anyone to understand. It does not use anything else, does not use TensorFlow or anything whatsoever, but it tells us that we can achieve, we can build a neural network and literally train in this way to achieve our training accuracy, right? And we will see that how TensorFlow takes this to another level altogether. This is definitely not a scalable model or not a scalable framework. This is just for us to understand, but that's what it is. I hope we are clear about this. Is there any confusion, question? I think it will be great if you have some questions. Awesome. I will share this thing if you need it. I will share this. It's not a problem. Okay. Okay. I think what we will do now is we still have about 20 odd minutes to go, isn't it? Should we ask notepad file? What is this notepad file? The code is same as most of this kind of projects. This code is same. No, this code is not same. This code is not same. This code I will share. Okay. This code is something that I can share. Not a problem. Okay. And what is the notepad file? Okay. This one. Okay. This is yeah. The IP1B file I will share. That's not a problem. The Jupyter notebook I will share. Assisted notebook that you already have. Only thing that I will share is this MNIST Python NN from scratch. Okay, this is something that I can share. That's not a problem. I think there's some problem with the Google Drive link, if I'm not wrong. Okay, I will have to pass this to the LMS support, and they will share it with you. Don't worry about it. Exactly. Now let's talk about it. That most of the time 5 and S look same. How do we define? The good thing about it is that S is not a class for us, right? So I think there will be no confusion at least. So, but suppose you have a list of class, you are trying to detect both alphabets and numbers. So basically 10 numbers and 26 English alphabets, then you might be a problem, right? Then there could be a way that it's possible that the machine might get confused. But if you give it enough sort of levels, I think it should actually overcome that problem, right? Okay. Let us do one thing. Okay. Let us understand where we are right now. Okay. From what did we do? Okay. And where we will go. Okay. And maybe we should ask some basic questions before we move ahead. So let's see what we did. Okay. We actually did backward propagation in a very simple manner, right? We have not spoken about loss and optimization, and let's do this now, and let us take the rest tomorrow, because I want to this part is done basically. Okay, the backward propagation here, what they are showing is that in this slides the backward propagation is shown with an example, and you will see this. This is nothing but chain rule, and this we can explain it. This is just one other way to do it, and we can explain this. Okay, and apart from backward propagation, what do we have? So this is backward propagation, and then we have activation, various activation functions. What does activation functions do? Okay, and then what do we have here? And that's about, so we have backward propagation in detail, and then we have activation functions, and then there is, oh, that's about it, right? And then we have regularizations. Good. Okay, so we have regularizations and its importance in neural network, because neural networks by definition are prone to overfitting. Okay, and you have to add regularization layers to handle it. It is very important. Okay. Okay, so basically we are left with three detailed topic. Okay, we have touched upon what is the core fundamentals of neural network, how do we do this, and what we can do tomorrow is go through this, definitely go through the loss function. Okay, this is very important. Okay, the error landscape, right, the cost function, and we can go through this, and then we can take it up. So what we can do now is that let's do some Q&A round, okay, and then try to find out, hidden problems rather than hidden features that you might have. You might have some questions, and we can discuss this before we move to the other deeper topics. Because can we do the backward propagation? Yeah, absolutely. Yeah, we will do that. Absolutely, we will do that. We will do it tomorrow. Okay, we will do that backward propagation with on tomorrow, right? The only thing is that, let me just see what is the examples here. So this is the backward propagation example is what we did, right? We can, yeah, so we can do a via slice. So this is not a problem. We can do via slice. This is all. I was thinking that it would be easier if we can actually codify it, and that's what we did. But I think we can do it via slide. That's not a problem, right? There's a question here. How do you explain TensorFlow loss and optimizer? Okay. So most common loss function is, even in neural network, is categorical cross entropy. Essentially a version of cross entropy, right? Cross entropy is something that you have used in your classical machine learning also, right? Even both, in fact, right? Log loss is nothing but binary cross entropy, right? As well as categorical cross entropy. Both you have used. So that same loss function is used here as well. So there is no special consideration of loss function in TensorFlow. Okay, it might be a different implementation, but that's about it. But it is exactly the same loss function. What is an optimizer? Okay, since we are discussing this, let's see the landscape of error itself. What is an optimizer? If you look at the loss function, right? Typically, so this is how a loss function looks like, right? If you actually see a loss function, right? If you are in, again, the parametric world, right, where you have one function, you are drawing a line y equals to mc square. What does a loss function looks like? Can anyone tell? What is a MSE? R square, right? All of them does a square, right? Why does everyone does a square? Y square. So if you see, why everyone has some square in the loss function, right? Can anyone tell why it is square? Because it allows us to create parabola, right? No. Yeah, positive number, but loss function is square, right? Right, there's an R square, then mean square error, right? Everything is square. You have a SNS, right? Sum of square. So to get rid of negative, yes, to some extent, but more importantly, to create a plane like this, sorry, to create an image like this. Oh yeah. Okay, so okay. Why do we need an image like this? There is a special mathematical property of an image like this. This is a parabola, a part of a parabola, an arc of a parabola, right? What happens is that if you have a convex area, this is a convex, right? And the other one is concave, right? So if this is your loss functions, most of the squares will actually give you a parabola. And geometrically, it is easier to compute what is the minimum. What do we need is that if this is my loss function, looks like I need to reach here, and this here indicates the place where my loss is minimum, isn't it? So I can traverse, I can create algorithms which can help me to start from here or wherever it is and reach here. In most of my classical machine learning problem, you have a function like this, and this generally is always one. Okay, you have one such convex area. But did we understand this construct that why a loss function is convex mostly? And that is a mathematical property because it is easier to deep dive and find the lowest point. Geometrically, if you ask me, if I ask you what is the lowest point, you can straight away go here. You don't say that this is the lowest point. You will never say, nor this is not the lowest point. There is basically for a parabola, at least a part of a parabola, there is only one lowest point, which is this, right? And and the objective function of that loss is that reach go to this place. How can you go to this place, right? That is what we are trying to say. In neural network, it's little tricky. Why it is tricky? First of all, it is not parametric. Second of all, the parameter space is so large, the function does not look exactly like this. The function looks something like this. Okay, it's a valley. Okay, it's a valley from, and you are looking from a top. So there are lots and lots of places where you might feel that okay, you have reached a loss. However, there might be another place which is much better place to be, right? So the concept is there is a local loss or a local minima and a global minima. From overall error landscape, there is generally one global minima, and that is where you ideally would want to go, but there can be many local minima. And there are many times what happens, neural network loss optimizers get stuck in this local minima. The algorithm which allows you to traverse here is nothing but gradient descent, and we can actually talk about that in detail whenever we have time. Essentially what it means is that don't go up, you are going down on the gradient, and at some point you will reach which is the lowest point, right? And we will talk about gradient descent if you have time sometime, okay? But the point here is that it's not that easy here, because even if you reach here, how do you know that there is this point which is actually lower than this, right? So in neural network, that is one of our toughest challenge, and hence we employ a lot of strategies, and then there are other optimizers which help the core, the vanilla gradient descent algorithm to reach to a global minima. And there's a lot of places what happens, you get stuck here. You get stuck here. In fact, if you start training a neural network, you will see that in the first epochs, right, you have drastic decrease of loss. Sudden, not sudden, there's always going to be a drastic decrease of loss, and then it started to plateau. Because what's going to happen is that here it is finding loss and that is happily staying here, and then it has to go a steep up, right? It feels that no, I'm fine here, why will I go here? Because it does not have the full landscape. Right? So that is a big problem in computing that final loss. From us point, if you have to see the whole of error landscape, it's very clear this area is nothing but the global minima, isn't it? Right. So the idea of deriving this gradient descent, and why we are going descent, you can also flip it up and say that go up, right? But I think it was mathematically easier to go down, find the lowest value. Also, if you go up, how far you will go? What is up, right? There is no limit of up, but there is actually a limit of down if your scale is from 0, right? 0 is the lowest that you can go. So that's it's a mathematical convenience. And two, if you just rotate the, if you just, you understood what I said, right? If I have this and you say that why will we go up, why can't we go, why are we going down, why can't we go up? You can go up, but there is no scale, there's infinite, right? How far you can go. So but you can go only to as low, and you can say that up to 0 only my scale is. That's the reason why we go down. That's the reason we go against the slope, right? We just, if the gradient is up, then you go to the up. Gradient essentially means what? What is the English definition of gradient? If you actually see gradients, right? What is the English definition of gradient? Oh, not like what do you mean by gradient? Okay. Uh, so gradient means rate of inclination, right? What means? No, rate of change. I'm saying English definition, right? Rate of inclination. Where do you incline? It can be high or low, right? It can be high or low. It's basically gradient tells us what is your degree of inclination. What, right? It basically gives you your rate of ascent or descent, right? In the slope. That's the reason it is called gradient, right? Rate of change is the output, of course, but since we are going by a valley, it's all slopy, right? And it's like, there are lots of peaks and, crevices. That's the reason we will use this logic, this algo called as gradient descent, right? So it's overall, the idea is very simple. It's overall decreases its error. However, look for local gradient, direction of change, go to the opposite direction, right? That's what it does. And if you have a error function like this, and you have to reach here, your objective is to reach here, right? So initialize a random point, right? And then you go towards the other way around, because you take a step towards the direction of the largest increase, isn't it? And then repeat the whole process till you fall really hard, right? You go down. The next step is lower, so stop here, right? So this is the gradient ascent. We actually, if you flip it, our objective is to go down. So what we are trying to explain here is that here, can you find out that are you going up or not? If you are here, we were doing gradient ascent. Find out which way is up and take a small step towards that. Okay, if you are higher than the current state, then you are going up, right? And you can compute that whether you are higher or not. Okay, and then continue to do that till you start falling, and the moment you start falling, stop there. And if you flip the whole thing, that is what we call as, gradient descent, is that you start going down and try to find out what is your lowest descent. If you are going up, then please go back, go to the other way around, right? That is what the gradient descent is all about, right? So however, there are few things that you have to worry about, is that the steps that you are making in the curve, right? The steps that you made, right, in the curve, in this line, how big you are making a step. If you are making a too big step, it's possible that you might cross the whole barrier, right? You cannot make a too big step, right? So that you miss it and you make a mess out of it, and then you have to again go back. That's going back is difficult, and that step is controlled by a very, very, very important hyperparameter called as learning rate, and you have to know this hyperparameter very well. Okay, and lot of time you have to start tweaking the learning rate. Learning rate is one of the very important hyperparameter in across any neural network. Generally, you start with 0.001 or 0.01. Okay, 1 of 100 to start with, right? We will actually go through this again. Don't worry, and we'll also look at the backward propagation example. And here, if you see, right, just to finish it off for today's topic, you will see that we are using something called as chain rule, right, to compute what is my weight, what is the change of my weight that I have to do given my error, right? We will actually look at that first thing tomorrow. Okay, I think we have about 10, 6, 7 minutes left. Let's open it for Q&A round, and then see that how do we reciprocate and basically come back tomorrow. Do you have any questions that you want to answer till the things that we have done? So what did we do today? We've actually understood the neural network on its own, right? And we have unraveled what a neuron looks like. We have understood that there is an operation of our forward pass at a linear layer. Something happens in linearly, and then some things we have to do non-linear. There are multiple types of non-linear functions. I don't have the Google Drive link. Please, I would suggest please raise a support ticket, but as I understand, the Google Drive is not working, is what I've been told. Okay. And then we also have gone through backward propagation, the forward pass and backward pass, right? Every layer has to implement it, and we've understood that these are all large matrix operation. So it's not that they happen at a neuron level, right? And we can optimize this. We've understood that um, the sigmoid functions, multiple types of activation, and we will look into that tomorrow when we close this thing. We have gone through how can we create a neural network without anything, no framework whatsoever, with whatever knowledge you have from with NumPy and Panda. It is quite simple, but we still have to understand some parts of it, like how does one compute gradient and so on and so forth. That we will look at tomorrow, right? I think we should stop for the day, but if you have any questions, we can start. We have 5 minutes. We can discuss some questions and regroup tomorrow to close ANN, artificial neural network. I'm just opening it for question. If you have any questions, please share. I'll figure it out. Don't worry. What I'll do is like I will ask I will ask the LMS team to arrange it to share it. Okay. What you should do is like all of you must ensure that you are on practice labs, and please ensure that in the self learning, if you have access to all the all the courses classes. Right. So what we did today is that we did backward propagation 50%. We will do tomorrow the rest 50%. We will do activation, and we will do optimization, regularization, dropout, right? And optimization is what we started right now, but we will discuss some more. And regularization we have not discussed. We will do that tomorrow. It will take us back to machine learning, and we'll see what is the dropout layer, which focuses on regularization for neural network specific. Okay. So for tomorrow, we can do. I'll figure it out. What is so the course end project is MNIST, and this is MNIST classification. I think you should start ready for this. So if it gets end tomorrow, then you should start doing it. The dataset is accessible here as well as the lab itself, right? Please understand that there is, if you see the messages from LMS, we are not supposed to have WhatsApp groups and personal communication. Okay, it's again simply on policy. Please check out the policies once, please. Okay, before sharing something in the chat. Remember that this session is recorded. Okay, and it's it's going to be very difficult if you share personal information. Otherwise, don't worry. I'll figure out a way to share it. I think what I've been told is that Google Drive is not operational. Okay. No worries. Are we all good? Do we understand till the point that we have done today? Is there any confusion at a basic level? Do you think that we are going slow, that we should speed up things? I'm open to ideas and how to make this experience better. Please let me know. Please send us feedbacks on this. I think this is going to be important. The reason is that I think if we get this core fundamentals right, again, how many lines of code that you're going to do? TensorFlow is 4 lines. But the thing is that if there is a problem that, if I ask you that if there is a misclassification, right, here, if there is a misclassification here, you have predicted actually 7 and predicted is wrong, 8. How will you debug, right? That is the most important thing that you should ask yourself, and that is the reason that we need to understand it very, very well. So the code files are all same, right? It is there in your self-learning page. Okay? Again, right? It's all there in your self-learning page. The only code that I have is that which I'll share, okay? And that is something that is not part of your curriculum. You can look at that at your own pace, right? But the course curriculum is same. You can just go to your self-learning page and just get this assisted practice demos. This is what we went through today, right? Perceptron. Yeah. Okay. Is there any other questions, folks? Let me know if you want to ask any other questions, or else let us close for the day and we meet again tomorrow. Please request you to ensure that your Jupyter notebook, your course materials are all ready. And if you are not ready, please reserve a ticket. As usual, if you don't have any questions, let's wrap it up today and let's regroup tomorrow and finish these things. Oh, there are lots of books. Okay. Shall we take this thing tomorrow? Let's remind me. Okay. Remind me. There's very good book on actually in deep learning. Just remind me tomorrow. I'll give you some books. Okay, on this. Thank you, folks. Thanks a lot. Appreciate it.